So yeah, so if you are while instruction satisfying one of the or if you have true copy is true for any of these check case, then conservatively adding 3 copy in while instruction. For example, before loop entry and add loop body start and add loop body end. So for example, if you're the conservatively copy adder judges or think that, oh, this while could be at risk, and I needed to add a copy instruction, then this while instruction will be changed something like this. So if you look at it, so before while, before calling while, this here is the one that we need to add a copy. The second is like after param, the last one is like before returning tuple. And also it adds like control dependencies like the control predecessors and control successors. And the second is conditional instruction. So it's, if you run the data flow analysis, there's something method called phi, which means you have 2 value for conditions. So for example, if you run this instruction and branch true and branch first, you see this value of condition have 2 values. One can be p, the other can be add, and we call this as a phi. If it is phi, then we add a copy before this root. Yeah, copy and copy. And there are third case like send and receive. Also, there are kind of a few conditions. One is like, so if you have a send instruction, and if send instruction is used by more than once, then the X-ray think that, oh, this is not a pattern that I know. What I know is just like one receiver, one sender. If you have 2 receivers, then it try to not add a copy because it's not a pattern that I know. For example, in this case, the sender is used send on and tuple. In this case, it doesn't add a copy.
So it will be undefined behavior.
Yeah, kind of. I just trust users, kind of. I just trust the code. I just trust code writer to write this code.
So the send on is just built-in function that is indicating that the send is, so this data will not be used in some communication, or like what is sent on exactly?
Actually, there is. I also not know that exactly, but what I assume is like if you have a send, and this is a sync operation, and every sync operation has a start and pair of start and done.
Yeah.
So if you run send, it doesn't actually wait for the send is finished. At the time of this function is called, it waits. But before this, send could be, it doesn't know whether this is, for example, you can think of it as a kind of a counter launch function. So GPU counter function invoking could be like a synchronous operation, and you don't wait at the time of calling this, right? So at the time of, so if you sync some kind of data before some operation, you need to add this. Then it's wait until the send is done. But yeah, actually, for me, like I didn't meet the function that uses send or send done yet. So, or also I'm kind of confused with the infeed and outfeed too. I didn't actually doesn't have a code that uses those operations. So yeah, I
What is the return type of send? Is it like Boolean?
Token. There's token type. One of the print type, kind of predicate integer or something like that. This token is is one of the GKX premium type, but I didn't use it before, so one of you guys could answer to me later.
Okay.
Maybe CPU, if you involve in CPU, you'll be use this. And also in the case that the send is immediately done by the next operation, which means this is synchronous operation, then it doesn't actually try to add copy instruction. And third is like, if your communication is outside a loop body, and it also doesn't care. It only cares the pattern that in outside while loop body sending something and the other loop receiving something, or other case. While loop body sending a case and inside the while loop body receiving this kind of pattern. And also if you find a send or receive, and if you don't find send done and receive done in your computation or module, then it give up, like, because it doesn't know this pattern, so it doesn't try to add, because it might give you unexpected situation, because start and done always, or send and receiver always paired. Otherwise, the other device like send and you don't receive this data, then it always hang. And so prescription for this case have two cases. One is for send, the other is for receive. Yeah, it's obvious before sending, you need to copy. Otherwise, in the middle of sending, you shouldn't touch data to be sent. So before send, if you are conservative adder, decided to, oh, this should be the copy instruction should be added, then copy will be added before send, and add a control dependency between copy and send. Control predecessors with a copy data and control successors with a send. For receiving case, almost saying as soon as receiving your data, the copy will be there. And the other is like in place operations. Also, there are how many conditions? 3 conditions, right? Three conditions. So if your backend support in place, I mean, if your backend support that this buffer can be shared, in that case, you can pair the X-ray using, I don't know which attribute, but there's a way to tell the X-ray compiler that, oh, this buffer is actually can be shared, then it doesn't add a copy instruction conservatively. On the other attribute, you can control the behaviors like GKX disjoint read write visions. So if this front end attribute is true, I think JAX will add this attribute, I guess, because the front end, I guess, is about JAX or PyTorch or TensorFlow. If you add this attribute, then it doesn't try to add copy conservatively. The third is like if you have buffer, so there are 2 cases, first and true. If your instruction only has single user, which case there's no need to worry about the data corruption. For example, if you think about add and dynamic update slice, parameter used by twice, add and dynamic update slice. So for example, in this case, if P is used by more than 1, then that could be a danger case. In that case, copy is added conservatively. But if you look at like this, P is only used by this guy, then it doesn't try to add copy instruction. So yeah, to reserve this, if you have any in place operation, then you're going to add a copy before this in place operation. Like that. Copy will be before instruction, will be before in place operation. There are a couple of in place operation. One is dynamic. If you look at the data flow analysis, Oh, yeah, kind of this. Scatter is one of them. If your instruction is one of them.
안녕하세요.
안녕하세요.
5분만 시간 써도 돼요?
여기 앉혀요?
뭐 여기
어.
지금 나머지 없어요?
안 계시긴 합니다.
아예 없어요?
그 주마님은 재택이시고 저만 있긴
아,
한데
그래요?
어떻게 하면
아,
이게 좋을까요?
아니야 괜찮아요.
아, 네네.
네네. 저 이번 주에 있을 때 같이 있으면 준범이 없는 건 아니니까
아,
준범이 저희 갔죠. 스페인.
맞아. 내일 오실 거예요, 주마님. 주마님은 24일인가 오시고.
그러니까 걔 없었다고 나머지 그 한 분 더 대표님인가?
네, 맞아요.
이 두 분이라도 있으면 제 있으면 저한테 잠깐만.
아, 네네네, 알겠습니다. 내일 연락드리겠습니다.
5분만 있으면 되니까.
아, 네네, 알겠습니다. Yeah, so yeah, if your instruction is one of them, then you need to add a copy before this. This is the 띵? So next one is like, so yeah, now if you run through this conservatively adder, now you have a code with a full of unnecessary copy, and you need to remove. And also I forgot about this. The reason why the X-ray chose this way is because it's more difficult to add a necessary copy instruction in the code. It's easy to implement, like you add a copy conservatively and remove redundant copies. Easy way to resolve this situation. So that's why they chose this strategy. So yeah, so as a part 3, now we have a lot of unnecessary copies and you need to remove. First one is like, because there are a lot of unnecessary like copies, so which means if you have a tuple and if you have a tuple, and if okay, let's see. So in order to copy tuple, you need to have a add like get tuple element to copy the inside of buffer inside, and then you need to construct tuple again, and then you need to use this instruction instead of this original one. And if this looks redundant, right? And if you remember tuple simplifier will resolve this. Tuple simplifier actually removes pattern where the get tuple element before tuple, and the other case tuple before get tuple element. If you have this kind of redundant tuple conversion, then tuple simplifier will remove. And then if you remove, then this custom code uses original tuple instead of this. And then DCE will remove the unused code. So after applying, the graph will be more compact. So that's why tuple simplifier is needed. And the second is like, we need to know which instruction is executed first. We need to know the order, because why this process is important, like depending on ordering, we're going to have a analysis that knows like the live region of each buffer. So depending on the computation order, we know that, oh, this instruction will live until from certain part to certain part, with a notation of def and final use, which is the defining instruction, which is the final instruction that uses this definition. So in order to have this kind of analysis, we need to know ordering. And this ordering has a kind of couple of few relations between two instructions. We can know like which instruction will start before some instruction, or which instruction is executed after instruction, or I don't know which one is executed first, kind of. So yeah, yes. But if you have an existing schedule and ordering, it knows the better ordering, it knows the better copy removing strategy. It can do better performance. So if you have a schedule, we're going to reuse this schedule. But if you don't have it, then we're going to create at runtime. And now we'll talk about that. Yeah. Then how do we remove copy and merge copy? That's another question for this presentation. And the way to removing copy is like using a linked list kind of. So for example, we're going to use a linked list, and this linked list is linked list for buffer. So every node, you can think of it node as a value. So buffer, if you have many values for some certain buffer, you have many nodes, and these are linked circularly. So for example, if some certain buffer is used by 3 value, then it's connected in this way circularly. If you have one value for one buffer, you have one node in circular connected. And if you have remove of a copy like that, because add is defined here, add is used here, and there's no this buffer for add, there's no collide with another buffer. There's no instruction that use this buffer, and copy is defined here, copy is used here. So if you decide that the buffer for add and buffer for copy can be connected, then if you have this linked list and there's a function that try let copy, if this function returns true, which means like, this buffer can be merged together, then the buffer is merged like that. Originally, there are 2 linked lists, and after this process, there's only one buffer can have 2 nodes with each node denotes value. So yeah, so let's go to the 3.4. So before, so to decide whether this buffer can be merged or not, we are going to use something like sandwich theory, kind of. So at every instruction, at every region, or function body or Y body, or maybe you can think of it as just function body because there's no region in H row. Everything is contation, and you can think of it as just function body. So across instruction, across the function body, we're going to analyze relative location. So we're going to analyze definition and final use for every instruction and for every reason. So, so how do we compute? Like, it's kind of caching. It has cache inside, but H-row ordering. If you run H-row ordering for 2 instruction, you have you get this one, whether this value actually have the same instruction, or one instruction runs before instruction 2, or instruction 1 runs after instruction 2, or I don't know which one is ordered first, or instruction 1 and instruction 2 runs independently. We know this relation, and in this mechanism, or the copy remover, he only renames this to kind of rename kind of. So if the instructions are same, then same instruction. If we guarantee that, make sure that some A instruction runs before instruction B, we say, before start iteration or after end iteration, or no overlap, or before start or after end. If we determine that between 2 instructions, if duration of 2 instruction is before start or after end, we say that, oh, there's interference and we couldn't remove copy. We can remove copy only for before start or after end or no overlap. So in real world analysis for while loop, so if you look at this, so because if this while loop is determined that as a like to be added conservatively adding copy instruction, then resulting computation will look like this. And in here, what we care is like, oh, I think I should have added a copy after this. Though, let's say, so this is the candidate for interfere. In terms of Y instruction, whether we can remove copy for body add is the question for this. So for example, Y is defined here, and the last use is like, sorry. Target for removal is this, sorry. So this is interferer, and Y is defined here, and including safety copy, the final use will be this. In that case, whether these copies can be removed or not, this is the question for copy remover. So is it safe to remove safety copy and have result, which is body add or Y directly, or can result can use Y directly? That's the question for copy remover. So analysis will analyze that it depends according to the sandwich theory. So actually there are two more conditions there, but for simplicity I removed, and it just say, oh, if the defining OP code is Y instruction, and the entry two is interferer, is this interferer the Y body, the parent or the function body belongs to Y body, then it says that it's safe to remove. When it is first, there's no interference. In the case, this copy is removed, kind of. So the case that I covered in the first section will be handled inside the copy remover class for every cases, and they are this kind of if loop, or just based on the analysis between instructions. And if it says that, oh, this is safe to remove, then it will remove copy. Also, the conditional branch is same. So as I mentioned earlier, conditional branch will, because it has a two different value. So every branch have a different, every branch have a copy inside. And in the end, if you see in this case, this P main is never used after condition, then it says, oh, P main is no longer used and it's safe to remove, and it tries to remove copy for those cases, or for both cases. But if the code uses P main later, then could be like side effect, and then it just remain this copy, kind of. In place operation, as I mentioned earlier, we have a copy before in place operation. And according to the sandwich theory, let's say, if you look at this, the P0 will be read by DUS, and the same buffer, P0, will also be used by dynamic update slices, and the buffer is collided, have a common section, common lifetime. In that case, it determines that, oh, it's unsafe to remove, so it just leave it as it is. If you have a distinct lifetime, then it's going to remove, but if the lifetime is collided, then it just leave untouched. Of the cases from 1 to 3 is so using the analysis between instructions. But the last example is like the case that uses like analysis between regions. So, for example, in this case, init 0 is defined here, and init 0 is used lastly at final use. And target for remove is like this copy. And this one is the instruction that try to modify. And we cannot know if we don't have like analysis between region to region, because the region is different. One is inside the main region, the other is inside the body region. That's why we need a analysis between regions. This is the case that we need a, yeah, I skip. And yeah, we almost there. But if you remove one copy, then you can unlock another chance to remove copy. That's why it tried to iterate many times until there's another header is added. So there's kind of fixed iteration. So it doesn't go infinite loop. So it stops until at some certain moment. So there's no boundary. I forgot the name of anyway, it has a fixed iteration, because every copy remover unlocked another opportunity to remove copies. So it keep going and going. And final check is like, now we need to handle like special cases. So why we need? Because there are two special rules. One rule is like output buffer must be unique. So for example, in this case, so negate and negate is not distinct. So we need to, so after all these processes, if you have this remaining cases, then we're going to add this copy. Another is like read-only buffers must be copied before exit. In this case, parameter const or something like that. So we need to copy. That's all. That's about the copy insertion pass.
딱 1시간